Hi, my name is Chris Versteeg, and I'm here to talk to you about our new NeuroAI course entitled Characterizing Computational Similarity in Task-Trained Recurrent Neural Networks. Starting with a little bit of background, what is biological and artificial computation? And so the rise of deep learning has led to artificial neural networks that can solve complex problems at near or even superhuman performance. The classical example of this is chess engines, which in the 90s started getting much better than humans. But it was recently advanced to do more complex things like classifying images, or even with the rise of GPT models, very complex things like maybe taking the SATs. Interestingly, the activity of these artificial neural networks trained to perform tasks can often resemble the activity of biological neural circuits involved in similar tasks. And so classically, if you train an artificial neural network to do image classification, the activation of that network tends to look a lot like the visual regions of the brain. However, we currently lack a principled method of comparing the underlying computation across biological and artificial networks. So that's going to be the goal of this project. And to do this, we're going to need to understand a little bit about a thing called dynamics. Dynamical system theory has recently been utilized to great effect to provide a set of tools for describing and quantifying neural computation. Dynamics, in just a simple one-sentence definition, are the rules that describe how the state of a system evolves over time. And to give a simple example, you could imagine a simple two-dimensional dynamical system just being this point that moves along this two-dimensional plane in just a circle like this. And just the state of this system, the location is determined, how this location evolves over time is determined by these arrows, which would be what we call the dynamics of the system. Interestingly, when we look at recordings from the monkey motor cortex while it's doing a reaching task, and we essentially just plot their trajectories over time, we can see that it appears that these single trials follow trajectories through state space that look like they are following a pattern of dynamics very similar to the one, well, maybe not very similar to the simple dynamics, but of the same character as these simple dynamics shown on the left. And also, when we train this artificial network to perform this task and look at the latent activity inside of this model, we can see features in this activity that looks like they follow rules, a very interesting set of rules that at a high level resembles what's happening in the motor cortex. And so to help make these comparisons more concrete, I've developed with some collaborators the code package known as the Computation Through Dynamics Benchmark. The Computation Through Dynamics Benchmark is essentially a tool base that allows us to train artificial networks to perform simulated tasks. At a high level, the features include task environments of increasing complexity, various dynamics models that can be trained on those tasks, functions for visualizing and interpreting the dynamics of these models, and metrics for evaluating the similarity. So now I'm going to talk a bit about the task environments that we have provided for you. First is a task called the 3-bit flip-flop. And this is essentially inspired by one of the first papers that did this sort of thing, Susilo and Barak, 2013. And 3-bit flip-flop is a pretty simple task. Essentially, all that matters is that you just get this noisy set of inputs. There's 3 inputs here, color-coded. And I want you to keep your eye on this purple input right here. And you can see that at this point, you get this input pulse, this pulse up for a very, very brief period. The state of this system should just increase when it receives this input pulse, and then when it receives a negative pulse, which you can see here, it should go back down to 0. And so essentially, if you just follow along this input trace, whenever there's a downward pulse, it goes to 0, and if it's at 0, it stays there. Every time there's an upward pulse, it goes to 1, and if it's at 1, it stays there. And there's 3 different states. And so there's 3 different bits. So essentially you can think of 3 on-off switches is all that this system is doing. And when we train a model to do this, we're essentially just saying, given this set of inputs, produce this set of outputs. That's all we're doing here. Just training a model to do that. And when we do this and we look inside this task train model, we can see that the way that this system has learned to do this task is that it essentially has 8 vertices, 2 to the 3rd power is 8. And so it just treats it as a cube. And the state just moves along the edges to the corners of this cube. And so that's the 3-bit flip-flop. The second task is known as, we're calling a random target task. It's based on MotorNet from AliCodeAll. And the way this differs from the 3-bit flip-flop is that whereas the 3-bit flip-flop takes in a set of inputs and it just tries to produce the outputs, and it's trained essentially to minimize the error between the output of the model and the goal, the random target task does something different. The random target task looks like this. It's essentially a model that is trained to bring the hand to the target when the go receives a go cue. And just an R and N that's doing this task, and an arm. So there's R and N, and there's an arm. The arm sends the initial state to the R and N. So essentially, where is my arm at the beginning of a trial? The R and N also receives context inputs, which essentially are what is my goal? And the RNN's job is to produce a set of actions that will affect the arm. And so the actions affect the arm, the sensory inputs change, and you get this loop here. And this model is trained essentially to minimize the distance between the endpoint and the desired endpoint. But because there's this feedback loop, these dynamics are much more complex and potentially much more interesting and biologically plausible than the simple 3-bit flip-flop. In addition, we have environmental inputs, these blue arrows, which essentially just are little force perturbations that displace the hand. So there's actually something coming from the environment as well, just to make it a little bit more complex. And these are the sorts of data that this model produces. You can see that the hand moves to the target. It produces interesting looking muscle activity to do so. And these are just the inputs that are coming into the model from these 3 sources that I talked about. Okay, so I've talked a bit about the dynamics models, RNNs, in sort of a black box way. What is actually available to you? What's available to you is something called recurrent neural networks, or RNNs. They essentially are trained to model dynamic systems, to processing inputs, to produce outputs. And that sort of generally at a high level looks like this. It takes in inputs, it's got a hidden state called H, and then it produces outputs Y. The important part of an RNN is essentially there's this function here, F, that takes in this input and a hidden state, which is just a state that's inside of the RNN itself, and use it to update the hidden state. So you can think of this, if you want to, as an unrolling process, where at time t gets x of t, you're at h of t, it uses x and h of t to produce h of t plus 1 and gets the next input and just slides along the process like this. There's specific model architectures that define what exactly this F update looks like, but they're beyond the scope of this introduction. There's very good resources online. At a high level, we're going to be providing 2 different types called the gated recurrent unit, or GRU, and then vanilla RNNs. Okay, visualizations and metrics now. What tools do you have to actually inspect these models? The first tool is known as a fixed point analysis. And fixed points are essentially just points, locations in state space where there are no predicted changes in the state. And so if you think about the 3-bit flip-flop, when you're at a vertex or a vertex of the cube and you're not receiving any inputs that say you should move around, it means you should be stationary. And that's what we see. So these green points are stable fixed points, which mean that if you were to drop the state there, it wouldn't move. The problem with this fixed point is that it's not really quantifiable in an easy way. And so for that, we're going to use what's called state R squared. And so state R squared at a high level is just, imagine you've got two versions of dynamics. One of which, called Model A, is this wavy ring here, and another called Model B, which is this flat ring. If you were to just do a linear affine transform, which essentially try to rotate, scale, and translate one of these to try to put it right on top of another one, how well could you do that? And for this example, this little toy example, you can see that Model A predicts Model B quite well. If you just were to flatten it along this dimension and then rotate it, you could predict Model B from Model A quite easily. But going the other way, Model B to Model A, you could rotate this thing so it's sort of along this dashed line, but you can't actually, in a linear way, sort of deform it like this to get something that looks like Model A from Model B. And for that reason, the state R-squared would be low. And so this is just one of the metrics that we're using. Another one is called dynamical similarity analysis. It's from Mitchell-Osterel, which actually is sort of invariant to the geometry, the specifics of the geometry of these two models, and looks more at the underlying dynamics themselves. Okay, so now that I've gone through what's available to you, talk a bit about the tutorial notebook. In the tutorial notebook, you will download a RNN that's been pre-trained to perform the 3-bit flip-flop task. You'll get code to train your own RNNs to perform 3-bit flip-flop and 4-bit flip-flop tasks. You will visualize the fixed point structures of your trained models and compare the representations using state R-squared. Finally, just very high level, explore the random target task environment so you can begin to train your own models on this. And with that, I want to say good luck and have fun.